Okay, the recordings is on, so let's begin. What we are talking about so far, we are talking about fundamental approaches to machine learning. And machine learning was a method for solving a variety of important problems, such as prediction or classification or recognition. And I introduced you with a very basic ideas on how can we do that. And at the same time, as several of the methods that I was mentioning on were developed, also there was a concept, an idea to develop one more approach to machine learning. And this approach was based on our knowledge on neural system operation. So the premise was quite obvious. We know that our nervous systems are composed of neurons, and as we are intelligent, at least we consider ourselves intelligent. So one of the ideas on how to solve problems was to try to mimic what our nervous systems do. So the premise was the following: if I can learn what exactly is a neuron. So what is a neuron? What is its functionality architecture? And how these neurons are arranged into networks. So if we can understand these concepts, maybe we will be able to create intelligent algorithms. So from research and knowledge on neuron and networks of neurons, we were hoping to build intelligent systems or these AI systems. And since one of the attributes of neurons and neural networks is that they learn, we are still in a domain of machine learning. So we are still with machine learning domain. And this concept has been initiated in 60s, in the last century. So it has a very long history. And it was one of the competitors among different machine learning or artificial intelligence algorithms. Neurons were considered as devices or concepts that will be able to solve a variety of different problems. So we were, the people were hoping that neural networks will be able to realize all these prediction tasks. And for prediction, we had or regression. We already had several counterparts existing. Also for classification, we also had several different counterparts, competing ideas. So neurons were just one more competitor. It was something that has been developed as another approach, mainly to cope with these problems. So what is a neuron? Part of this today's lecture is something that some of you probably know quite well, because this will be a review of the material that has already been presented during earlier courses, and some of you attended these earlier courses. But nevertheless, I have to introduce it from scratch, so I hope you won't be very bored. So what we know about neurons? Living neurons are just cells. The cells, like any other cell, is composed of several functional parts. And in neural cells, the computational intelligence and machine learning is interested with a functional perspective of what this cell actually does, how it operates. So modeling of a neuron is in what I'm going to briefly summarize. Modeling of a neuron is done from this perspective. We are not interested in any physical, deep processes that take place in neurons. We are just focusing on how it operates, because we would like to make a model or a piece of an algorithm that will be used for processing data. So what data are being processed in real neural networks or using neurons? Neurons are cells that accumulate charge and produce or not produce spikes or discharges of discharge. Or a train of electric pulses. So over time, if you measure a potential over one of the parts of this cell that is called an axon, and we can, from the functional perspective, identify it as an output of a neuron. So at this output, over time, we will have trains of pulses. So this is some voltage, and obviously this will not be just Dirac pulses. These are some continuous smooth functions. Or continuous smooth spikes, but this is just a schematic diagram. So there will be bursts of electrical pulses produced by a neuron, and the rate of this firing. So a neuron over time. So this is not zero. This is just some time t0. The rate of this firing will be proportional to activation of this neuron. So the activation is just a capacity of generating neurons and of pulses, and this capacity of generating pulses is a result of accumulation of a charge here in a cell body. Here is a cell body. And this cell body will be accumulating a charge, ions. And where does it charge comes from? It comes from other neurons that are connected to this unit that I'm considering through interfaces. I will talk about these interfaces in a while, but in general, I can say that here I have some other neurons output that is providing this neuron with its output electrical pulses. Here is some other neurons output that produces pulses, and so forth. So a neuron will be inputs, and here are inputs to these neurons. I can to this neuron. So this is input 1, let's say. This is input 2. This is input 3. Or this is 2. This is input 3. This is some input 4, and so forth. And the neuron can have many inputs. The typical number of connections between neurons is at the order of hundreds, at least in our nervous systems. So a neuron will receive stimuli from other neurons. Outputs of neurons will be fed to inputs of other neurons. And information that neuron processes can be thought of as this charge that is being delivered or drained from a neuron. Because if I have this cell, I can either deliver charge or I can drain charge. So I can either inject charge or ions, or I can remove ions. And these processes of inserting or draining are dependent on something that is one of the most interesting components of a neuron, which are synapses. So at every input, we have something that is called a synapse, and the synapse is so here is a synapse, and here is a synapse. And this is a structure that is performing very complex, in quite complex way, a kind of transformation. Because if I have a neuron that is generating these pulses, each such a spike is a bunch of ions. And depending on what is a character of this synapse, these ions will be either forwarded to a cell body. So this is a cell body. This is a neural cell body. So these ions can be forwarded to the interior of this cell body, but the amount of these ions, amount of charge, will be modulated by the synapse properties. So if I am injecting, if a neuron from some external neuron at this input, if it delivers 3 different ions, a synapse can transfer to a cell body, for example, 2 ions, or it can transfer 1 ion, or it can transfer 3 ions. But there is more. If on some other input we have a neuron that is active and is delivering charge, a synapse can be arranged in a way that if this input neuron is delivering 3 ions, positive ions, a synapse can cause that from a cell body 2 or 3 or 1 ion are being drained, taken away. So these are 2 different types of synapses. This synapse is called inhibitory. So that is the first kind of a synapse. Inhibitory means it will be trying to reduce a potential of a cell body by draining its charge. And the second synapse, this one, can be called as excitatory. This means it will be contributing to increasing a potential of a cell body, electrical potential of a cell body. And if this electrical potential exceeds some threshold, so this electrical potential, let's name it Q. If this electrical potential at some time instant t exceeds some threshold value theta, then a bunch of ions is being produced and sent to the output of this neuron. So this is a very, very simplified understanding of the processes that take part in a neuron. A neuron is a device that is accumulating charge, and this charge is provided via synapses from all the units that are connected to this neuron, all other neurons. And depending on a potential of a cell body that is accumulator for a charge, if this accumulated charge exceeds some level, a neuron is just producing a pulse. And the rate of this firing depends on how fast the cell body's potential is increasing. If there is a lot of activity that is excitating this neuron, then a neuron will generate pulses at high rates. If there is a small activity of these neurons that provide a cell body with a charge, it will be generating pulses at much lower rate. And at the extreme situation, if this inhibitory mechanism overtakes, a neuron might be silent because it might not exceed this threshold level at all. And all the neurons are exactly the same. So the neurons, they have exactly the same architecture and exactly the same functionality. So if a neuron is this circle, the structure of a neural network would look like this. And this neuron obviously feeds some other neuron. So I can say that with arrows, I have outputs of neurons, and without arrows have inputs of neurons. All these neurons are exactly the same. So our structure is homogeneous. So this is one very salient property of a neural network, because this is a homogeneous structure. And also, all these neurons work at the same time. There is no any time clock that controls activity or synchronizes operation of this circuit. Everything works in parallel. So if some would like to provide you with the highlights on what is the most important property of an architecture of a neural network, is its homogeneity and parallelism. And this architecture, this structure, will process information. So we can look at this as a computer. That also processes information. We have some input data, and this input data are turned into some results. A neural network is doing exactly the same. It processes input information, and it is producing some results of its operation. So we can say that a neural network is an alternative computer. It's a biological computer, but its major properties are very different than of conventional computers, because conventional computers are not homogeneous in their architecture. We have specialized units in a conventional computer architecture, and also conventional computers do not operate in parallel, even if they are parallel in terms of having several processors or several graphical processing units. In fact, each of these components is working in series. It executes some serial code, serial in time. So neural networks are very different. This is a very different approach to information processing. And I would like to introduce how do we model these networks. We'll begin, obviously, from a single neuron. And we will see that we can quite well interpret what exactly these neural networks do if we consider some particular architectures, some particular patterns of interconnections. For some of them, we will be able to very clearly explain what exactly is going on in such a data processing structure. So let's begin, obviously, with a single neuron. So now we have this single neuron. So our objective right now is to derive a model of a neuron. What is a model of a neuron? Obviously, a computational model. This is something that I am interested in. This is what is of interest for machine learning. What is a computational model? The first thing in deriving a computational model for a neuron is to decide on a form of information that is being processed by neurons. So I told you that in biology, this information can be thought of as something encoded in firing rate. Firing rate is something that encodes information. If neuron is very active, it means that its stimuli is very strong. So what we can say, we have neurons everywhere in our data processing circuits, including sensory neurons. So a sensory neuron that is sitting, for example, in our eye is a photoreceptor. And if it sees a lot, if there is an intensive illumination, this neuron will be strongly excited. And it will be, and I'm sorry. That means that there is a lot of information to be sent to all the successors. So I have the information is something that is proportional to a firing rate. But the problem in computations, if I would like to model a neuron, if I would like to write an algorithm that is processing this information, a form of spiking data is something that is completely incompatible with what we are doing. Because what we are doing in computations is we are manipulating numbers, values. So the first element in creating a computational model of a neuron is to assume that not the firing rate, but just real values, so real numbers, will be considered as information that is being processed in a network. What does it mean? It means that I can assign here a value and here a value and here a value to this activity. So, for example, here the reasonable thing will be, let's assume that this is a zero activity or zero information that is going to be communicated. And here will be 0.5, for example, and here will be 1. Why 1, not 10? Of course, I could come out with 10, but one of the properties of neurons is that there is some maximum firing frequency. Maximum frequency or maximum firing rate. Let's maybe use the term rate. So neurons are biological systems, so they cannot produce pulses at an arbitrary rate. So there will be always some maximum rate. So if there is something maximum, then I can say that the firing rates can be from 0 to some maximum value. So 0, it means no firing. and maximum is the maximum capability of a neuron, and that's why I'm free now to assign a value to this maximum. And customary people decided to say that the maximum value or maximum activity of a neuron will be 1. And at the beginning of research in neural networks, it was assumed that the minimum is 0. Later on, several of these assumptions have been relaxed, changed, but we will begin with such a very, very simple approach. So what we have is we have a unit. A neuron will be a unit, so this will be a neuron, and I will be providing this unit with information from other neurons, and this information will be real values from the range 0. So x will be a value, and this will be a value x that is generated by a neuron that is connected to the first input of this neuron. X2 will be a value that is connected to the second input of this neuron, and so forth. And if it has n inputs, there will be n numbers, and each number will lie in an interval from 0 to 1. And obviously, a neuron will be outputting a value that also will belong to the same interval. So from the point of view of information that is being processed by a neuron, we will be using just real values. A domain for every input will be just an interval of real values from 0 to 1. And so if I would like to be more specific about this box, I can say that what do we have in a neuron is a neuron will begin with input information that is being delivered by other neurons, some other neuron. And this input information for the first input of my neuron will have an index 1. And this will be something that will be subject to operation of this synapse. So this synapse I will here depict as a triangle. And the synapse will be a module that is going to transform this input value in a way that is similar to what real synapses do. And what do these real synapses do? Well, they can either modify the amount of information that is being passed from input to the cell body. There will be a cell body somewhere. So this will go to this cell body. And this modification can be mathematically very conveniently modeled as just multiplication. So this synapse, I will name it as a weight because this is a role it plays. It modifies or changes a value of x1 or is weighing a value of x1. So it has a name weight, and this weight will be again a value that belongs to, that is a real number. It can be positive, and if it is positive, then I can say that this weight is modeling excitatory synapse, because it doesn't change a character of operation. Because if I'm delivering something, something proportional to it goes to further to a cell body. But if it is negative, then I'm inverting a character of operation. If I deliver something, actually it drains me something from a cell body, because I have a negative component. So my neuron if I would like to depict it in a more detail, will look a little bit like this. There will be a series of inputs, and each input will be fed with information from some other neuron, and each input will be weighed using multiplier, which I call weight. And after this multiplication, I will have a modified or transformed input information. So it will be just a product of input and weight. And all of this now will get summed or accumulated. So I can say this is an accumulation unit. And this is something that I can say is modeling a process that takes care in real neurons in a cell body. I'm accumulating all of these contributions. And once, so accumulation of these contributions is just computing a sum of these components. So what is being computed here? I will tell that this is a value. I will name it S. A letter S comes from the name of this variable, because I can say that this is a state. This is a state of a neuron. At some particular time, a neuron has some particular state, and the state is just a current level of activity, or current level of its activation. And this state is just a sum of products. So if I would like to write this down in a compact way, if I have n inputs, I can say this is just a sum of products between inputs and weights. And this can be, in the simplest model, it can be seen as an output in absolutely, as I say, the simplest possible model. I can say that the neuron is something that is producing just an output of this form. If I assume that, I'm saying that my neuron is a linear device, because this is a just linear transformation it's a linear transformation of an input. In fact, to be a legitimate linear transformation, I would need to add here something like b, for example. So I can say that here I might have also another variable that is a bias, that because any linear transformation should include also a bias. So a bias is just another parameter of a neuron, just like W1, Wn through Wn. This B or a bias can be also considered as a parameter of a neuron. But a linear neuron, so I can say that this is a linear neuron, and this is a hypothetical device, because that would mean if I am having a linear neuron, that would mean that its output, y, can be unbounded, because it can be any real number. And this is not in line with biology. I would like to come out with a device that is modeling this biological neuron. And biological neuron is a neuron that can have only, that can have just a bounded range of possible output activations, or it can generate either nothing or some maximum value. So its output needs to be bound. It's not that I can come out with this linear simple model, because this linear model is unbound. So what is being done here is an introduction of another step of processing, and this another step of processing is something that is called activation, or activation function, or output function. Activation function that is attempting to provide that output values belong to this interval 0, 1. So if I would like to propose a candidate for this f, because output is some transformation of S, that means of a state. And a possible candidate for implementing this activation function is something that I have already introduced you, because it needs to be a function that squeezes values, from that are initially cover the whole range of real numbers to an interval 0, 1. So a possible transformation is, for example, a logistic function, or a sigmoid function, or logistic function. So sigmoid is any function of this shape. Sigmoid, a name comes from the term that this is S-shaped. It has a squeezed S shape. And among these sigmoid functions, what we have this logistic function that we were talking about, and which can have, for example, this formulation. So logistic function is one of the ideas on how to squeeze output values. And if I adopt this perspective, or if I adopt this function, I can say that now I am providing a viable modeling of a neuron, of a neuron's functionality, because I'm capturing in this model, I'm capturing all what is relevant to information processing. My neuron is receiving inputs, and these inputs will be bound from between 0 and 1. And each input is subject to weighting. And this weighting can be either excitatory or inhibitory in its operation. That means it can either just modify a value, or it can both modify a value and the sign of the input information. And all these pieces of modified information are then summed up, and then they are subject to squeezing function that is trying to ensure that my output, a range of output values produced by a neuron, are also bound within this interval 0, 1. So basically, this is a model. If I would like to mathematically describe a neuron, so a neuron will be a device that is computing this expression. So from I equal 1 through n, because I have n inputs, and here I can say that I have this additional bias, or a threshold value, and I can say that a neuron is a computing device that I can summarize using a mathematical formula, where f could be just a logistic function, or it can be some other nonlinearity. I will comment on this later. But now we stick with something that is the most basic. If you look at this formulation, you will notice that obviously what is a sum of products? Sum of products is obviously a dot product. So basically what I can say that if my variables, if I will write them as vectors, as column vectors. So if my x variable will be a variable that contains information that is being presented to a neuron, if my weight vector contains information on all synapses or on all weights, then I can say that what a state of a neuron, at least part of this state without this bias, I will be with this bias in a while, it is a dot product of these two vectors. So recall that basically all of the methods that I was presenting you previously, all of these methods for implementing different machine learning tasks, they had these dot products in their formulation. If it was a linear regression, we were computing dot products. Logistic regression, we are computing dot products. Linear classification, we are computing dot products. Neurons, we are computing dot products. So as you see, dot product is one of the most handy, most useful, and most often exploited concepts from mathematics in machine learning. One more modification that I'm going to introduce to simplify my description of a neuron is that what is a state of a neuron? A state of a neuron is a result of this sum. So this sum is W1x1 plus W2x2 plus, then comes the next product, and then comes B. But I can say that B is 1 times B. So what I can do is I can extend my vectors. So I can make extension to these vectors and add 2 more components here. So at the first position in the parameter vector, I can add B, and in the first position of my x vector, I can add 1, and I can say that my activation, my state of a neuron is just a dot product of this, and now it becomes a blue W vector and blue x vector. So I can say that this is a state of my neuron. So using this simple notational modification, I can say that my neuron basically is a device that can be defined as some nonlinear transformation f of a dot product between weights, and this weights, in fact, this is a parameter vector. This is a parameter vector. So these are parameters and inputs. So a neuron is just a very simple device that transforms information, and this information is given as numbers. So it transforms numbers, a vector of numbers, and produces a scalar value. And production of this output scalar value is a nonlinear transformation, and it can be a logistic function, transformation of a dot product between inputs and parameters. So basically, this is this model, because this is a model, a functional model of a neuron. and this model has been proposed by McCulloch and Pitt, McCulloch and Pitt. So these are two names, and this is called McCulloch's or McCulloch's-Pitt's neurons model, and this has been proposed in I don't know 50s in the last century, and it is used as a basic the most general formulation of what a single neuron does. So I hope this is clear. So I will be talking about neural networks, but now I'm still with a neuron. What is a neuron? A neuron will be a component of this data transformation algorithm that is attempting to mimic or to model real neurons operation. And this unit is extremely simple. At least from the point of view of mathematical notation, it is just a very, very short formula. What is really interesting from the point of view of neurons operation, and what should we conclude so far from what we have just what I have just presented. So for example, if assume that my neuron has two different inputs. Assume that my neuron has two different inputs, x1 and x2. There is this sigmoid function is a function that basically is computing a dot product between these two vectors, and what I can say that this will generate output values according to this, obviously, to a formulation of this function. So this will be continuous values, but if my outputs, if values of my state will be greater than some value here, some s plus, and here lower than this s minus, I can say that this neuron is producing a kind of a binary decision. So if s are lower than s minus or s are greater than s plus, I can say that basically a neuron can be considered as something that we could that we could call a classifier, because this is a classification function, and how can we graphically visualize that? A dot product is just a line. There is a line equation. Yes, we have a line equation that says that W transpose times X equals 0. It's just the line equation, and basically this is this parameter vector is a vector that is perpendicular to this line. So what I can say that just this single neuron, what can it do? It can provide me with data classification. What I can do is I can say that a neuron is a very primitive, simple algorithm for data classification. And results of this classification depend on how this line is being located in this space. So if red and blue are samples of two different classes, so if my neurons' weights are given and produce this black line, I can say that this neuron will be correctly classifying these classes. Obviously, I can have a neuron that have a completely different set of weights. So Again, this is some other neuron with some other weights. And for this particular weight vector, I will not be able to correctly perform this data classification task. So, as should be obvious to you, whether a neuron can correctly perform a data classification task or not depends on how do we choose its weights. But again, this is something that is probably quite obvious to you, because what I am talking about is I'm talking about something that we are talking before. I was just using a name theta for a parameter vector, and we were considering, for example, logistic regression or classification, because logistic regression was basically a classification task. And what I introduced is I have shown you that I can train such a or this logistic regression algorithm can just learn to separate two classes using, for example, a line. And this learning means choosing appropriate parameters. So it's exactly the same here with a neuron. A neuron is characterized by this weight vector, because weight vector, this weight vector is something that makes this particular neuron individual. It is something that defines a neuron, and if I choose the right parameter vector, it, for example, can solve this classification problem that I have just drawn. So the most interesting and the most important in a theory of neurons and in a theory of neural networks is how neurons can learn, or how can we train a neuron to perform required functions. And the function that I am interested here is, for example, data classification. So from what I said so far is that I have a neuron. A neuron is just a concept of data processing, and it involves a dot product between its parameters and inputs. And I can look at a function of a neuron from the perspective of data classification. Obviously, I can look at its operation also from a perspective of regression. But so far, let's stick with data classification. So I would like to train my neuron so that it can actually perform data classification. And how can I do that? Well, again, it is nothing new as compared to we have already presented. Because the main question, the main problem in neural network research is how neurons learn, how neural networks learn, but how they learn to let's say, useful functions. And learning useful functions is something that is going on with us through all our lives. Some of our functions are already hardwired, because our hearts beat, we breathe, and we produce different enzymes and so forth. But many other tasks we learn. And how do we learn? We learn exactly as we were talking before about learning. We can learn in several different scenarios. For example, we can learn in a supervised way. So this is a question mark here. And here I say we can, for example, learn using a supervised setup. So supervised setup means that I will be presenting some samples that have labels. So I will be presenting a vector of inputs to a neuron with an appropriate label, and I will be having a set of such examples. There will be many examples, and I will be expecting my neuron to learn to classify them correctly. To classify them correctly, that means to assign appropriate or to produce appropriate labels if it sees something that is similar to one of these training examples. So that's one of the ways that neurons learn. They can obviously learn also in an unsupervised manner. We are not talking so far about unsupervised learning. We will talk about unsupervised learning in maybe in 2 classes from now. But just to have this list complete, that's another way that I can learn weights. So this learning useful functions is I can make it equivalent to learning weights or parameters, but I will just use said weights. So it can be done in an unsupervised manner, or it can be done in some approach that is a mixture of the two. So if I would like to train a neuron or learn neurons' weights, I have several different possible ways to go. So we'll be talking about now about this supervised setup. And we'll be talking with this again will be something that is closely resembling what we have already said, because this is not a novel concept. It is a concept that we are already introduced and that has been around before research on neural networks emerged. So in this supervised setup, basically what I'm going to do is I'm going to present a neuron with a set of vectors. There will be training vectors. Some training vector xi I will be presenting to a neuron. So this is my neuron, which has n inputs, and it will be producing some output, but I will know what is a target. A target, maybe here I would, instead of using y, I maybe better could use it's not a vector, so I'm sorry. So I can use it here instead of a letter y. I can use a letter t. However, I think it is not introducing now confusion. So a neuron will produce me with a value y. And I know that my examples, so let's make examples blue. So these are my examples. So this is x, and this is my target value. And a neuron, initially, let's say it is being born with completely random weights. So it does know nothing about the task that it is supposed to solve. So if I would like it to improve, what I can do is I can use this scheme that we were using in our previous methods, a scheme of defining some loss. I can define a loss. So if this is a sample I, it is a loss Li, and this loss can be defined, for example, as a mean squared error or a squared error between what I would like to get, or ty, minus what I get, squared. So this is if I would like to present this or accumulate these losses for many samples, so let's assume that I have 100 samples, so my I goes from 1 to 100. I had 100 examples. I can obviously also compute the loss for all of these samples, and then this loss will be just a mean squared loss. So this will be Ti minus Yi squared. So this will be just this simple MSE measure of performance. I think it doesn't require now much elaboration because it is nothing new. So what I have is I have examples and I have a parametric algorithm or parametric transformation. So my examples are input vectors and labels. Parameters that I have is a weight vector, and I have a transformation from X to Y, and I would like this transformation to be as close to a desired one as it is possible. So this loss is something that is evaluating how good this transformation is. And if I would like to correct, if this is incorrect, what I can say is that, again, this is something that we are talking about. If I would like to see how to improve some weight K of a neuron so that it works better, then I can say I should make a step which will be in a direction, and let's say that this is just one ith example that has been presented. So let's make it a superscript. So this is an example I. If I would like to improve, I should change this weight so that it reduces a loss. So this is a general expression that says that if I would like to reduce a value of a function L, and the function L obviously needs to be a function of the weight Ik. I means at a time instant I, and K is a kth. So this is my neuron, and I have here x1, and somewhere here I will have xk, and there will be here these weights. And this weight that I'm interested in right now is here. This is WK, and there will be more neurons up to the n. So I'm interested in figuring out how to improve performance of a neuron, and I would like to. I know that if L is something that measures performance, and the lower value of L means better, so I want to minimize this function. And to minimize a function, I should change an argument so that it goes in the opposite direction to a derivative of L with respect to the parameter that I'm interested in. So basically, this is a formulation that we already have. And what is even more convenient is that basically we are ready to very quickly solve this problem, to be specific, because we are doing very similar thing already. So what is my loss? My loss, once again, is just a squared difference between what I expect and what I get. So what is what I get? What I get is a result of transforming of my input example using my parameter vector. So this is what is y, and my parameter vector contains my weight wk, and now I am supposed to compute a derivative of loss with respect to this particular parameter. So we have a compound function. So Li is some function g sub wki, because it depends on w. And g is just a letter that is trying to make it compact. So basically, this g function is composed of first level of composition is that my value of the parameter that I'm interested in sits inside y, and y basically this is a state. So the second level of complexity is that it sits inside S, and inside S I have this dot product. So I have a composition, and I can say that the product is just a derivative of this external function times. So if I would like to just to make it more clear, so let me write it once again so that it's very clear what I would like to oops, something to tell. So my derivative of my error with respect to my parameter ik is my derivative of this error function with respect to this external layer of my composition times a derivative of this external level of my composition with respect to a state times a derivative of a state with respect to my parameter, because there are three levels of composition before I get to this variable that I'm interested in. So it is 2 times ti minus yi and times minus 1, just because y was minus. Now there is a derivative of, I can say that yi is f sub si. This is a transformation of a state. So I will just tell this is f prime. This is a derivative with respect to s of si times, and what is s? And s, I is just a dot product. So let me this time write this dot product as just in an explicit form from n as maybe not I but j wj times x I j. So a dot product we have here, and a derivative of this dot product with respect to ik is just x ik. And the last thing that needs to be clarified is what is this derivative, and if our function is a logistic function. So if this function, if this f has this form, for example, we know that a derivative or dy with respect to ds is just y times y1 minus y, because we already had this exactly when we are talking about logistic regression. We just have exactly the same expression. So if I would like to sum this up, I can say that if I would like to make a correction to a parameter k, I need to make a step in a direction that is opposite with respect to a gradient of this function with respect to a variable that I'm interested in. And if I plug in this data, I can say that I have eta times ty minus yi times yi times 1 minus yi times xik. So it is nothing different that we had for logistic regression. It's exactly the same. If I would like to make an update to all weights, because observe that means that for kth weight, that what I will be using here, the only value that is specific to k is a value of the input at this particular input, a value at this particular input. So if I have this neuron, and if I have here my value, and here is my weight, and here is my value xk ki, and here is my weight wk. The only thing that is relevant to information that is provided to the input is a value at this particular input. So if I would like to tell what is an update for the whole vector, whole parameter vector, I can say that this is just eta times ti minus yi times yi times 1 minus yi. All these are scalar values. And finally, I have xi, which is a vector. So to conclude, what I can say is that I have a formula for training a neuron with a logistic function. Obviously, this part is specific to a logistic function. If this function has a different definition, this will be different. But a logistic function is very friendly for differentiation. So, and it is very extensively used. At least it was frequently used in neural networks. But this formula is called a delta rule. A delta rule. Basically, it is something, or sometimes it is just shortened to this this way of this convention of naming. And this delta rule is a rule for a supervised training of a neuron. And I think it is something for you quite absorbable. I think it is quite clear. So if I have a neuron, and if I have a training set, and the training set, okay, 2, there is a question about 2, and the good that someone is paying an attention. So I had 2 here. I've observed that here I had 2, and when I plugged this into this equation, I forgot about this 2. But as eta is a parameter, and here is eta is some number, So I can say that 2 times eta is some eta prime, and I have this eta prime here, and this prime, it doesn't matter. So this 2 basically doesn't matter. But thank you for this pointing this out, and I encourage you to interrupt if something is not quite clear. So what we have is we have a delta rule, and the delta rule is a recipe on training neurons' weights. And training neurons' weights means trying to update weights so that I can solve a classification problem. because this delta rule is closely related to solving classification problems. Also, it would also work with regression problems, because loss can be defined exactly in the same way. So if I have a neuron, so let's say that I have a neuron that is born. So it is born and its weights are random. And if I have a problem, a classification problem, and if I have a classification problem, means that I have data, I have a training data set, and if it is labeled, that means if I have information on samples and their targets, what I can do is I can train this neuron to perform better and better in an iterative way. So this is an iterative training. Why is it iterative? Just because my function is nonlinear, and I cannot solve it analytically. It is just like it was in logistic regression, linear regression. It's something that I can solve analytically. But if I have any nonlinearity, then I have to do an iterative training procedure. And this iterative training procedure will be a procedure where I will be applying to this neuron samples. First sample I will apply to a neuron, and I will confront this with a target, and I will make an update, and so forth. And then I present the second sample. I will compute the output. I will try to see how it works. If it doesn't work correctly, I will make the second update, and so forth. And after this iterative training, that should take several epochs. I hope to get a neuron that is trained. So I hope to get a trained neuron. So my neuron will have a set of weights that are now chosen, so that I will be trying to solve a problem as good as it is possible. So I think this is also for you now clear, because it is just like in logistic regression. It is just a different architecture of a device, because in logistic regression, what I had, I didn't have this visual or structural model for my algorithm, and here I have a structural model of my algorithm. It tries to correspond to some existing piece of biological hardware, and we just have changed the way of understanding basically the same of the same concept. So logistic regression and the neuron is something that is extremely close to each other. So let's move on. So is it clear? So what I have covered so far? I have covered the first thing is a model. How do we model a neuron? And the second thing, which is very important, the most important element of theory, is how to train a neuron, or how neuron learns its weights. And I'm presenting a concept of supervised learning. So this is one of many possible approaches, but this is something very practical. So I hope that these 2 points are clear. So now let's move on. If I'm saying that I have trained a neuron. I assume that I have trained a neuron. So I had samples, training samples. And again, let's assume that I had blue samples that are from one class, and I had red samples that are from the other class, and let's assume that I have a random neuron. So let's assume that let's say that the red is also here, and let's assume that I had a neuron that has been born randomly. So let's assume that it was its weight vector. So I will move a little bit this sample down. So let's assume that this is an initial weight vector. That this is some weight vector 0. I have a neuron that has been born this way. And now I begin my training. I begin my training, and if I begin my training, I'm applying samples. So let's say that I apply this sample, and let's assume that this is a positive side and this is a negative side of this line. So it is just like in logistic regression. I am saying that the target is 1. And for a negative side, I will be saying that the target is 0. If let's assume that my neuron corresponds to, let's say this will be a line. Let's say y equals. Just I begin with a very simple formulation for this line, and I will express it using x2 and x1 in a while. So let's assume, because it's so let's make it a little bit more interesting. So let's make it a little bit. Let's make it this way. So this is this line. This is positive. This is negative, and let's assume that this is 1/2x plus, let's say 1. So if I would like to use this dot product formulation, I will say that I have x2 minus 0.5 x1 minus 1 equals 0. This is an equation of my line. And let's assume that I'm presenting a blue sample. Just to make it simple, I'm presenting a blue sample, and it is supposed to be 0. So a blue sample obviously is located at 0, 0, and its label. So this is a sample. So this is a sample x1, for example, and this is its target. This is T1. So if I plug in the value of this sample to this equation, or what I have is I have -1. The result is -1. Result is -1. And this is I can say that what I'm computing here is my state. My state is a dot product between input sample and parameters. So what I see is that S is -1. That means my neuron, here is my neuron's output, is its state, and let's assume that here is -1. So I can say that my difference between target minus what is actually generated is close to 0. Observe that, once again, I will show you the delta rule. This delta rule says that an update to weights is proportional to a difference between what I have and what I expect to get times, and again here I will say SI times XI. So basically this is my delta rule. And my delta rule says here that the update is proportional to this difference. I can say that this is an error. This is just an error, delta. delta I. That means an error means a difference. So this is not a loss would be squared, but now it's just a difference. This is an error, and you see that the error, if my neuron was born with this particular parameter value, so my neuron's parameters at the beginning are 1. I'm sorry, this is -1, and then there is a component minus 0.5, and the last is 1. So this is this is W2, this is W1, and this is this W0 that is actually modeling this B, this bias. So if I present a sample that is correctly classified, then my update to weights will be close to 0. My update to weights will be close to 0. And this is reasonable. Yes, we shouldn't change anything if it works correctly. And the same will happen more or less when I will be presenting all the samples until I present this sample. Because if I present this sample, what will happen is my error. So let's say that this is a sample x5, and let's assume that this sample x5 is let's say 4 and 1. And my target here is 1. Target 5 is 1. So this is x1, this is x2, and if I would like to use this extended vector, and here is 1. I'm using this extended vector. So if you plug in these values, you will see that obviously what is being produced, the output or the dot product will be 1 minus 2 minus 1, that is -2. If it is -2, so y is approximately y is approximately 0, and my target was supposed to be 1, so my error 5 is around 1. So my error is around 1. So if my error is around 1, the vector will get changed. So I will get a change. And the change will be proportional to this expression. So it will be eta times 1 times f prime, which is it's not very fortunate as an example, because I will multiply this by something that is 0. But basically, what I get here will be something that is positive, a little bit bigger than 0, but it is positive because the derivative of this function is positive, because it's a monotonously increasing function. So my update to my weight will have exactly the same direction as x. So if a vector of this line is here, this is a vector w, and my x is here, this is my vector x5, observe that my update will be an update in this direction. So I will change a direction of this line. So you can see that graphically, because my update will be a vector, that the new vector, a new vector will be vector number 6, will be vector number 5 plus this update. So observe that after computation of this particular step, after this particular step, I'm sorry. Okay, the thing that I wanted to do is to use another color, and so my new line will most likely look like that. So as you see, this training is something that can be visualized graphically, and this training is something that enables me making steps, and each step I'm trying to improve, and actually this is something that occurs. And another thing that you can observe, that it strongly depends on this eta, on this parameter eta, because this parameter eta will tell what will be a magnitude of this change. So if this eta is chosen to be too small, I might not improve enough. Whereas if it is chosen to be too large, I might rotate this line in an excessive way, so that I might start making errors for the remaining points. So if you look at this from this perspective, you will see that one of very important elements is a choice of eta to make learning efficient. And typically a rule of thumb is that at the beginning we begin with some big eta. So initially we begin with eta. For example, what is big? It's hard to say, but for example 0.1, and slowly as consecutive epochs are executed, we are decreasing this eta, so that at the epoch number 10, for example, it will be 0.0.1. What is the rationale behind that? The rationale is that at the beginning, when most likely this line is completely off, I should allow for big changes of its orientation, so that I can quickly get to the right regime of its location. And after a while, I should become less sensitive to new samples, just because I need to be more careful, because if it is almost correctly located, I don't want the updates to be all updates to be too abrupt. So one of the conclusions of this simple example that hopes to illustrate training of neuron weights is that there will be training of a neuron and of a neural network will be something that depends on such parameters, and this is something that I would name a hyperparameter, because this is something that strongly impacts a performance of learning, but it actually cannot be predicted from data. We have parameters like weights, and they can be predicted from data. But also we have some parameters that we need to choose in a little bit different manner. And these parameters that cannot be estimated directly from data are called hyperparameters. So eta is the first hyperparameter that that impacts the procedure of learning, of training, of a neuron training. So a neuron can be trained in a very simple way. So a neuron can be trained in a very simple way. And after this training, what I can expect is I can expect that if I have training data that belong to different classes, then after training, my neuron will correspond to a line that separates clusters of this data correctly. The problem is, what if my classes are distributed in a way that cannot be separated by a line? So, for example, let's imagine such a distribution. Such a distribution is very often named an XOR problem. An XOR problem. XOR because it corresponds to kind of a logical perspective of looking at this distribution. That means that on extreme values, I have something else than in intermediate values. So clearly, if you look at this distribution, there is no line that can correctly separate these distributions. So what is a limit of usability of a neuron? A neuron can solve only problems that can be visually presented as clusters that can be linearly separated or separated by a line. And we call that neurons can solve only linearly separable problems. Separable problems. That means a single neuron is capable of learning weights and separating clusters that must lie on either of sides of this line, of this separating line. If clusters are distributed in a way that cannot be separated using a line, there is no way to train a neuron to solve this problem. So linearly separable problems are trivial problems. So these are trivial problems. Trivial because I don't need a neuron here. That's the first thing. A simple linear classification is also capable of solving this kind of problem. So and linearly separable problems are trivial because, in fact, I can always change a system of reference just by, for example, rotating this system of reference. Observe that I can rotate a system of reference so that one of these axes aligns with this direction and the other will be there. So observe that I can easily separate both classes based on just a scalar single component. This will be some psi1. That was my initial directions of my system of reference. But what I can do is I can rotate this system of reference. I'm not changing a problem. I'm just changing the way of its description. And observe that now my classification task is a task applied not to vectors but to scalars. And my task is to find a value so that all elements from one class have a value greater than this threshold, and all the elements from the other class have values lower than this threshold. So basically, even if I have 100 directions in my space, so every vector has 100 components, I can always, if the problem is linearly separable, I can always find just one direction. that goes through these distributions, so that all the projections of samples on this one direction will be numbers that are either greater of some threshold than some threshold for one class, or lower than this threshold for the other class. So that means that any linear classification problem is trivial. Trivial because I can reduce it to a problem whether I can find a value such that all values from one class are greater than this one, and all values from the other class are lower than this one. So linearly separable problems are trivial. Neuron can solve trivial problems, so a conclusion is that neuron is nothing really useful. And this conclusion halted research on neural networks for 20 years. Because the development, the history of development of research on neural networks, it began with the first formulation of this neurons model, then formulation of this delta rule. And then people had a lot of expectations because they thought we are using units that look like our cells of our nervous system. So we will be able to solve any problem that we can solve. And finally, they realized that what they can solve is solve a trivial problem. So they turned to other methods that were enabling us to correctly classify or correctly handle problems that are inherently nonlinear. And for example, in linear regression, you know that even though the formulation is linear, but I can come out with nonlinear, with polynomials, for example, that are solutions. I can find coefficients of high order polynomials that enable me to correctly fit some sequences of values. So people decided to focus on these other approaches where some directions on how to solve nonlinear tasks were already known, rather than spending time on neurons. And the solution to this problem was trivial. But we will be talking about this during our next meeting, because the time is up right now. So I wish you a good week, and that's it for today. So I finish